Good day, everyone. So for this video, we will be discussing another application of differential calculus. So we have here time rates. So when we say time rates, so those are the rate of change of any physical quantity with respect to time. Okay, and it is described by the derivative of the variable with respect to time. So say for example, we have any quantity, okay, represented by any variable. So its derivative, if we derive it with respect to time, so that is described as a time rate. Okay, so for problem solving involving time rates, we need to first, from the given problem, identify the given rates. Okay, and then assigning variables, and as well as drawing illustrations to establish the objective function. Okay, so the function uh, will be used in solving the problems. Okay, and then if we had already the function, so we will differentiate it with respect to time, and then after, so we will solve for the required, okay, in the problem. So say for example, so we have here our first example, example 1. So a spherical balloon is inflating at a rate of 27 pi cubic inches per second. So how fast is the radius of the balloon increasing when the radius is 3 inches? Okay, so for this problem, we are given with a spherical balloon. So let me draw a sphere. Okay, and the balloon is being inflated. Okay, so meaning it increases in size, it increases in volume. Okay, so its volume is expanding. Okay, and we are given that the rate of inflation of the balloon is 27 pi cubic inches per second. Okay, so this is a rate of change in the volume. It is increasing. The volume is increasing. So therefore, if we let V as our volume, okay, so if we let V as our volume, then the derivative of V with respect to time, okay, so this will correspond to the rate of change of the volume. Okay, and we are given that the rate of change of volume is 27 pi cubic inches per second. Yes, 27 pi cubic inches per second. Okay, so the required now in our problem is, oh, sorry, so the required now in our problem is how fast is the balloon increasing. Okay, how fast is the radius of the balloon increasing. So if we let r as our radius, if this is our radius r, okay, so find dr over dt, so the rate of change of the radius of the balloon at a given radius of 3 inches. Okay, so for our solution, we will now establish our function. Okay, so the function must relate the rates. Okay, so function relating volume and radius. Okay? So we must establish a relationship between the volume of the sphere and its radius. Okay? So that is very simple from the formula. So we have a formula for volume. So volume of a sphere is V is equal to 4 over 3 pi r cube. Okay? So next, if we already have our function, then we will differentiate them. We will differentiate the function with respect to time. Okay? So the variables here are the volume and the radius. So we will differentiate v with respect to time, and we will also differentiate r with respect to time. So therefore, dv over dt is equal to, so we have a coefficient of 4 pi over 3. So we write that 4 over 3 pi. And then differentiate r squared or r cubed with respect to t. So using the power formula, so this will become 3 r raised to 3 minus 1 multiplied by the derivative of r with respect to t. So that is dr over dt. Okay? And then we'll now have dv over dt is equal to, so we can cancel 3. So we'll have 4 pi r squared dr over dt. So since we are solving for dr over dt, so we can divide both sides of the equation. So dividing both sides of the equation by 4 pi r squared. Okay, so we can cancel 4 pi r squared in this side. So therefore, we will have dr over dt is equal to dv over dt over 4 pi r squared. Okay, so substituting our dv over dt, which is equal to 27 pi cubic inch per second, and our r squared, which is 3 inches. So therefore, we will have dr over dt is equal to, so is equal to 27 pi cubic inches per second over 4 pi, r is 3 inches, and then squared. Okay, so therefore our dr over dt will be equal to, so we can cancel out pi, and then 27 over 4, so 27 divided by 4, that is 27 divided by 4, it's 6.75. The unit will be, so we have here cubic inches divided by square inches. Oops, sorry, we still have 3 squared here. So it's 27 divided by 4 divided by 3 squared. Okay, so sorry, it's 0.75. So 0.75, so we have cubic inch divided by cubic inch per second divided by square inch. So the unit that will be left is inch per second. Okay, so that's it. So that's our answer. Okay, So what if we have r is equal to 4 inches? Okay, so the rate of change also of the radius will change. Okay, so that is because this type of rates are instantaneous. Okay, so these are instant. So when we say instantaneous, so those are uh, the values at that instant only. Okay, because as you can see, um, if you observe, if you imagine a balloon being inflated, okay, so if it is inflated at a constant volumetric rate, okay, its increase in radius as time goes by, it's the rate of the increase of the radius will decrease. Okay, so at first the rate of the radius is fast. Okay, so the rate of the increase of the radius is fast, but as the balloon gets larger and larger, it slows down. Okay, so that's because of the volume. Okay, so because we have a constant volumetric flow rate. Okay, so if you have a balloon at home, so you can try inflating it. So you will see that if the balloon gets very very large, so even if you what you call this, so even if you keep on blowing into the balloon, its radius, the change in its radius or the change in its size will be uh, small. Okay, so that's how it works. Okay, so let's have another example. For our second example, water is flowing in a conical cistern at the rate of 8 cubic meters per minute. If the height of the inverted cone is 12 meters and the radius of its circular opening is 6 meters, how fast is the water rising when the water is 4 meters in depth? Okay, so we have a given here. Our container is a conical cistern. Okay, and it was described here that the shape of a conical cistern is in the form of an inverted cone. Okay, so we'll have generally can imagine the cone. So we have an inverted cone. Okay, so let's say like that. Okay, and okay, so the shape is like that, where water is being uh, filled, okay, in the container. Okay, so the water is also flowing at 8 cubic meters per minute. So that is a volumetric flow rate. So we have 8 cubic meters per minute. So therefore, that is dV over dt. So we have dV over dt of 8 cubic meters per minute. Okay, and then we are given with the dimensions of the cone. It is said here that we have a 12 meters height and a 6 meter radius. So our height, so here we have our height. Oops. We have a height here of 12 meters. And then we have a radius. Okay, so the radius of the opening above. Okay, so let's say that. So this is 6 meters. Okay, so here we are asked to solve. We are asked to solve for the how fast is the water rising when the water is 4 meters in depth. Okay, so we are given a depth, okay, of the water. So say 4 meters is right here. Okay, so if we have a height of 4 meters, so determine how fast the water is rising. Okay, so how fast the water is rising will correspond to the rate of change of height with respect to time. Okay, so for our solution, so we are involved with the volume of a cone. Okay, so volume of a cone from our geometry, that is V is equal to 1/3 pi r squared h. Okay, so from this problem, okay, so we are given with the cone. Okay, so that's why our volume is 1/3 pi r squared h. Okay, so but the problem here is that our V is expressed in terms of two variables, r and h. Okay, so we need to express volume as a function of one variable only. Okay, so since we are required with dH over dt, so then we must eliminate r squared and express it in terms of h, or the height. Okay, so if we examine this, and then if we examine this, so say for example we take half of the cone. Okay, so we take half of the cone. So this is 12. Okay, so from here to here, this is 12 meters. And then from here to here, this is 6 meters. Okay, and then the height of the water at any time is h. And the radius at any time is r. Okay, then you can see that we have two similar triangles. So a larger triangle and a smaller triangle. Okay, for similar triangles, we can apply ratios. Okay, so take for example, in this case, we will take the ratio of r over h. So r over h, okay, the ratio of r over h of the smaller triangle will also correspond to the ratio of the radius and the height of the larger triangle. So the radius of the larger triangle is 6, and its height is 12. Okay, so if we simplify that, r over h is equal to 1/2. If we cross multiply h on the other side, so r is equal to h over 2. Okay, so with this relationship of r and h, so we can now substitute this with the r on the formula for the volume. So therefore, v is equal to 1/3 pi, r is equal to h over 2 squared times h. So simplifying that, it will become v is equal to 1/3 pi multiplied by, this will become h squared over 4 times h. Okay, so our v now will become, so 1/3 times 1/4, we have 1 over 12 pi, yes, 1 over 12 pi h cube. Okay, so now that we have expressed our volume in terms of one variable only, then we can now proceed with differentiating v and h with respect to time. Okay, so dv over dt is equal to, so writing the numerical coefficients, so 1/2 pi multiplied by derivative of h with respect to time, so we have 3 h squared times dh over dt. Okay, and then simplifying, dv over dt is equal to, we'll have here 1/4 pi h squared times dh over dt. So since we are solving for dh over dt, then we can divide both sides by 1/4 pi h squared. So therefore, our dh over dt will now become dv over dt, okay, over 1/4 pi h squared. Okay, so since we have our h of 4 meters, so then substituting, dv over dt is 8 cubic meters per minute, okay, over 1/4 pi, and then h is 4 meter squared. Okay, so this will become 8 divided by 1/4 divided by 4 squared, so that is 2, and then we have a pi in the denominator, so therefore dh over dt is equal to 2 over pi. And then the unit, so we have here cubic meters per minute divided by square meters, so what will remain is meter per minute. Okay, so that is now our rate of change of the height. Okay, so if you want to express that in decimal, so we have 2 divided by pi, so it's around 0.6366, okay, meter per minute. So that's about times 100, so 63 centimeters. Okay, 63.66 centimeters per minute. Okay, so again, if we substitute, if we have another height, so say 5 meters, so you will see that the rate of change of the height will also change. So because, as you can see, so imagine you are filling up a cone at a constant velocity, or constant volumetric flow rate. So you can see that at first, okay, the height, the rate of change of the height is rapidly increasing. Okay, but as you can see, if you reach the almost at the top, okay, so the rate of change of the height of the water inside uh, will start to slow down. Okay, so that's it. So it's instantaneous rates. Okay, so this rate of change of height is um, it's this rate of change of height is only at a height of 4 meters. Okay, so if we change the height, so say 5 meters, so this will also change, as you can see. So it will become 8 divided by 1/4 divided by 5 squared. Yeah, so you can see it will be different, 32/25.